All right, another problem. Let's take a look at this old problem. We got an inclined plane. You got a 10 kilogram mass on top of it. We got a 20-degree angle. Got some friction here. It's called the kinetic friction. So this thing's gonna slide. We're gonna make this thing slide. We got a 2 meter height that the box is currently at. Um, and let's not go the traditional route with this that you guys are used to, because you would have to do sum of all forces. You'd have to figure out the acceleration based upon friction and the component of gravity and all that stuff. Let's not do that. Let's talk about this in terms of energy. So if this thing starts at rest, what kind of energy does it have? And again, at the top we have potential energy due to gravity because it can get it can displace downwards. Gravity can work on it. So gravity's going to be working on it on the way down. Um, Now, what else is going to happen here? This thing is going to slide down and it's going to gain a certain kind of energy. It's going to gain kinetic energy, right? So down at the bottom, it should gain some kinetic energy, and we would expect the energy to go from potential to kinetic. But on the way down, something is taking energy away, right? What is that? And that's going to be friction. So whatever is going to happen, in the beginning we have potential energy. Here's our energy equivalence, right? In the beginning, we have potential energy, which is mgh, and in the end, we have kinetic energy, which is 1/2 mv squared, but we also have heat energy, the energy of heat due to friction. The friction is going to turn some of that potential energy, some of that kinetic energy rather, into heat. And so on the right side, we're going to say, hey, we have some work done by friction. Okay, so we're going to account for that. We got to account for all of our energy. In the beginning, we have mgh, then we have that equal to 1/2 mv squared plus the work done by friction. So just to keep on writing things in, we'll keep it in variable format for now. 1/2 mv squared plus the work done by friction, and we should know that the work equation is force times distance. Make sure that those are in the same direction. So force is going to be the force of friction, and that's going to be for some distance. And what distance is that? We're looking at friction acting, and friction is going to be acting that way, and this hypotenuse would be the distance. So that's kind of important. We need to know what that distance is. So distance d is equal to the hypotenuse, and that's kind of, let's see, hypotenuse, we got the opposite side of the angle, so opposite hypotenuse, that's going to be sine. So sine of my angle is equal to opposite 2 over the hypotenuse d. Okay, and so if I wanted to solve this, I'd move things around. Don't be too quick about it, because some of you would say, oh, it's going to be sine of theta divided by 2, and you're wrong. Okay, make sure you know what you're doing. So we're going to multiply both sides by d. We're going to divide both sides by sine theta. So it's really sine 2 divided by sine theta. And theta is 20. So d, grab my calculator, is 2 divided by the sine of 20, and that's going to give me 5.847, let's say 5.85 meters. Okay, so that's d. So back up here, we have m, we have force of friction. Force of friction's equation is 5.85, just to make sure we got it. It's right there. Force of friction is normal force times mu. So mgh is equal to 1/2 mv squared plus normal force times mu times d. We got d. We need that normal force. So we have an inclined plane. If we remember, we've got normal force going off that way. We're probably going to have friction going this way. So how do we get that? It's going to be this component. And there's our angle theta. And so normal force should be, I'm just going to do this a quick way because we've gone over forces. I don't want to go back and just figure all that again. Normal force is going to be mg, that's mg, cosine of theta. Okay, that's what I'm going to put into there. So my equation is evolving. It's turning into something. mgh is equal to 1/2 mv squared plus normal force mg cosine of theta times mu times d. That's my equation now. Turns out we didn't even need mass, did we? So cancel out mass. G h is equal to 1/2 v squared plus g cosine theta mu d, and we want v, right? So we'll keep on moving this around. So the potential energy in the beginning, if m was there, potential energy in the beginning minus the work done by friction should be equal to the kinetic energy that the block gets at the end. That's what we've done. So gh minus g cosine theta mu d is equal to 1/2 v squared, and we're just fully doing this out algebraically because some of you honestly still need practice with algebra. And we'll multiply both sides by 2, so don't screw up because we're multiplying both of these things by 2. And then we're going to square root that to find v. Okay, and so plugging in numbers, we've got 2g, let's make it 10, the h is going to be 2, and that's going to be minus 10 cosine of 20, multiply that by mu, which is 0.3, times d, which was 5.835, and that's all within this big parentheses, multiplied by 2, and we square root that. So let's see what we get. I'm going to take the inside first. So 10 times 2 is 20 minus 10 times cosine of 20 times 0.3 times 5.85. Hit enter. Multiply that by 2, and then I'm going to square root them. So this is all equal to 2.65 meters per second. So we just found the energy at the very bottom. Now, or rather the velocity at the very bottom. It's right there. Now what we could do is we could talk about energy. We could say, hey, how much energy do we have at the beginning? Well, we had mgh energy at the beginning, right? So the energy in the beginning is mgh. That equals 10 times 10 times 2. Well, 10 times 10 is 100, times 2 is going to be 200. That's 200 joules in the beginning. Okay? Well, in the end, what's up with our energy? Well, we got energy that's kinetic at the end, and we got energy that is the work done by friction to turn it into heat. So we'll just call it the work of friction. Okay? Well, what's kinetic energy? It's going to be 1/2 mv squared, 1/2, 10, v, 2.65, we're going to square it. So half 10 is 5, multiplied by 2.65, and we square it. So we got 35.11 joules there, just about. And then we got the work done by friction, which is going to be equal to friction, which was normal force times mu times d, the distance that it went. And we found out that normal force was mg cosine theta, and then we have mu and d. So what are our numbers? mg cosine theta mu 0.3 and d, which was 5.85. And so we got 100 times cosine of 20 times 0.3 times 5.85, and that's going to give me 164.9 joules. And that is pretty good because 164.9 plus 35.11 gives me about 200. So the energy in the end is equal to the energy in the beginning. And that's the proof. So that's law of conservation of energy. Energy in the beginning is equal to energy at the end. One more thing that we could do is we can talk about power. And we talked about this in class. Power is equal to work done over a certain period of time. Okay? So we can talk about the power, how much power we have for this object, and that's going to be work of different things over time. Now, it's going to take this thing a certain amount of time to get to the bottom, and we'd have to figure out what the acceleration was in order to do that. Well, let's see, maybe. What do we know? We know that the initial velocity was 0. We know that the final velocity was 2.65 meters per second. We know that the displacement, or actually the distance that it went, was 5.85 meters. And could we actually find the time using that? Let's see. We don't have acceleration. We don't have time, but we know we do have an equation to find acceleration. And hey, guess what? It's this one, which happens to be what we've been using for energy the whole time. So let's go ahead and use that. So the final velocity is 2.65 squared. Initial velocity is nothing. 2, A is what we want. X is going to be 5.85. So A is going to be 2.65 squared divided by 2 divided by 5.85. And that's going to be about 0.6002 meters per second squared. And 602 meters per second squared. And if I wanted to find time, I could by taking the first equation, and we have final velocity minus initial velocity divided by acceleration should be the time. Well, what's my change in velocity? Looks like I went from 0 to 2.65, so 2.65 divided by my acceleration, 0.6002. My time is about 4.415 seconds. Now, hopefully you didn't get lost there. We were talking about power. And in order to find the power output, or the power of gravity, the force of gravity, we need to know how much work gravity did. Well, how much work is gravity doing? Gravity is applying a force of mg over a distance of h, and so we have gravity 200 joules over a certain period of time, 4.415 seconds. Okay, so we can talk about the power of gravity, I guess. I'm not sure if that's the best way to put it, but in this problem, we have gravity, mg, the force, acting over a certain distance, h. And that's going to be equal to 200. That is 200 divided by 4.415 gives me 45.3. And the unit for power is the watt. Okay, and that's going to represent joules per second. Right. Now, what about friction? What is friction doing? Well, friction did 164 joules, 164, let's say 165. Friction did 165 joules of work. It was negative, though, in the same period of time. And that's equal to 37.37 watts. And then we also have this leftover. So gravity was doing 45.3 watts. Friction was doing 37.37 watts and taking it energy away. So 45.3 minus 37.37 gives me a value of 7.93 watts. So 7.93 watts is how many joules per second this thing was actually getting. And hopefully, if we take our last number, 35.11 joules, because that's how much kinetic energy it got at the end, right? Divide that by 4.415, hopefully that's equal. 35.11 divided by 4.415 equals 7.9. A little bit of rounding there, but there you go, 7.9 watts. So as far as the power goes, this thing got 7.93 watts per second. Gravity tried to give it 45.3 watts, or 45.3 joules per second. friction was taken away 37.37 joules per second, and in the end, it only got about 7.93 joules every second. So a little bit of power there. So if you ever have work over a certain period of time, you can talk about power, and we just did.